back to the memory management series of operating system. And today we are going to learn about paging. And in the previous video, we saw about the different non-contagious memory allocation techniques, among which we have just started about to discuss for the paging. We discussed about the PAS, LAS, frame, pages, and every sort of bit, but today we will just join all these dots that we have already done. So basically this lecture for paging does starts from this one only, but in previous video we just had a few introduction part, or we just discussed some of the terminologies that we will be using now. Okay, now in the previous video we discussed that first the CPU, just a second, let me draw it straight so that we can cover more things in such one page. Okay, so let's start. So in the previous video we saw that the CPU does not generate a physical memory address for fetching any instruction or data from the main memory. So the CPU generates, or the processor generates, an address called logical address. Now, I already told that we will discuss about this logical address in the upcoming video. So, in this video, we will be talking about what does this logical address signify. So, the CPU generates this logical address, which consists of two parts. And we saw that one part represents the number of pages, and the other part represents the size of each page, that is the page size. So let's denote that with P denoting the number of pages, and D denoting the page offset, that is the page size. Okay, so this is a let's say a logical address consisting of 13 bits, where let's say 3 bits are used to denote the page and 10 bits are used to denote each page size. Okay, now this logical address that the CPU generates needs to get converted into a physical address. Why? Because all our instructions and data and everything is stored into the main memory, so we are fetching our data and instructions from our main memory, not from our virtual memory or the logical address space. Okay, so this has to be mapped to a physical address, which will contain of some frame number and a frame offset, and this frame offset is equal to the frame size. Let's say this is 10 bits, so this is needs to be the same. Okay, this needs to be the same, and frame size will be 2 bits. So this 13-bit logical address has to be mapped to this 12-bit physical address. For this to be mapped, we need to we need this paging. So this paging is implemented with the help of some hardware. So in this paging we learnt about that we have a page table that maps our physical address with the logical address. So here we have a number of pages. Okay, in this page table we have this number of pages. So the pages is equal to this number of rows is equal to the number of pages. So if we have 2 raised to the power 3, I mean 8 pages, so for each page we have the corresponding frame number. Okay, for those pages which are present in the main memory. So this thing we will see in today's video. So just let me first illustrate what happens. Okay, so for this logical address, it is divided into two parts. So the first part I have already said that this is the page number. This denotes the page number. So 3 bits are allocated for page number and 10 bits are allocated for the page size, that is D, which is the page offset. So P denotes number of bits required to represent pages of LAS. I mean the total number of pages of LAS. LAS stands for logical address space, and it is also known as the page number. So 3 bits will denote how many pages? 2 raised to the power 3, that is 8 pages. Okay, so this means that in the LAS altogether 8 pages will be present, right? So for 8 pages, we will be having a different address. For example, let's say if it is 001, then it denotes that the CPU wants the first page. Okay, this one. So P denotes number of bits required to represent the number of pages of LAS, and it is also known as page number. Now, if we see of D, so D denotes the number of bits required to represent the page size. Okay, number of bits required to represent page size. Okay, it is also known as page offset, or you can also say it as word number of page. Okay, so which page number? So this is called the word number. So let's say if it is 000 something up to 10 bits, so this denotes the page offset, or it denotes the size of each page. What is the size of each page? So we'll see this D component later. Okay, let's come to the physical address, which constitutes of the frame bits and the D, that is the page offset or the frame offset. So F, so this is the PA. Let's say it is 12 bits physical address, and of this 2 bits denotes the frame number and 10 bits denotes the frame offset. Okay, so F denotes the number of bits, number of bits required to represent, required to represent the frames of the physical address space, frames of physical address space, or it is also known as the frame number, number of bits required to represent the frames of physical address space, or it is also known as the frame number. And D denotes the frame offset, or we can also say that it is the word number of frame, frame offset, or word number of frame. We are going to discuss about this D component in some moment in this video. So D is the frame offset or the word number of frame, or we can also say that D is the number of bits required to represent the frame size. Okay, now let's see what happens when a CPU generates this logical address. So how does this mapping occurs, and what is this page that we are talking about? What is the space size and frame size, and how the mapping happens? Okay, so this we will be discussing in today's video. So let's say we have this CPU. Okay, let's first constitute the virtual memory and the physical memory. So we have this memory called the virtual memory or the logical memory, whatever you call LAS. Now this LAS is divided is 8k kilowords, and then we have a physical address space, that is our physical memory, and it is 4 kilowords. Okay, now let's say for now let's assume that we have divided this entire memory into certain pages. So each page size is 1 kilowatt. Okay, so this will be same for physical address space, that is the PAS, and it is going to be the same for the virtual address space LAS. So it is divided into 8 part, each part containing 1 kW. Okay, so we are dividing it into 8 part, and this will be divided into 4 part, each part consisting of 1 kW. So each part will be having this address like this: 001, 010, 011, 100, 101, 110, and 111. So this is the address of each you can say page. So this is the page number, and inside that we are having the page that is 1 kilowatt page. So each page is having it is divided into 1 kilowatt page. Now what does this page consist of? It consists of a set of instructions or a set of instructions and data that is required for the program execution. So we have equally divided into 1 kilowatt pages, okay, and each page is represented by a page number. It's suppose similarly you can assume like a book with each page consisting of 1 kilobyte of data, and each page has a corresponding page number. So if you want to go to page number 5, you have to go to just fifth page, and you can fetch the data from the fifth page. So if you know that a certain data is present at the fifth page, you need to just go into the fifth page to fetch this data. That's what the processor does. So in the CPU we have this processor, and this generates whenever it wants some instructions to be executed, it generates a logical address. And this logical address, it does generates consist of two components. That is the page number. Let's say it wants to read something from the third page. So okay, so it will generate some logical address consisting of uh, like this. Okay, I think I went far. Okay, let me scroll down. So it will just generate some logical address of 13 bits. Why it is generating a logical address of 13 bits? Because this LAS is 8 kW. So total number of bits required to represent this LAS is 2 raised to the power 3 into 2 raised to the power 10 word, that is 13 bits. Okay, so that is why it is generating the logical address of 13 bits. Okay, so this is clear from the very first video. So here it is generating up something with a page number of let's say 011. So it wants to access this data, and in this data also, when it goes into this page, in this page it wants to access certain data. So that data is denoted by this page offset, that is D. So within the page, if you want to specify which address or which instruction you want to access, so you need to specify the page offset. So let's say it is 00000000101. So fifth line it wants to access. Now let's see about this page configuration. So each page is 1 kilowatt. That means 1 kilowatt means 2 raised to the power 10 into word. So each page will be constituting of 2 raised to the power 10 rows, and each row will be having one word. Okay, so this is one word. So one word, which word is fetched and required by the processor, will be represented by this row. For example, it is 0, 1, 2, 3, so on up to 2 raised to the power 10 minus 1. So this is called the page offset. Okay, so within LAS we have different pages, and for each page we is divided into this 2 to the power 10 row, with each row carrying one word information. So when the CPU requires this word of information from the third offset, it will mention it like this. Okay, so this requires this much information. Now it is clear this D component. Now it generates the logical address, but we it can't go and just access from this. It has to access from the physical address space. So now some pages are being bought from the logical address space to physical address space. Let's say this physical address contains 4 kilowatts, so it is divided into 1 kilowatt pages, 4 pages, and each page is mapped to a frame. So this is the frame number, and in each frame one page is placed. So some pages are being brought from logical address space to physical address space. So let's say in 00 frame, let's say we suppose place P7, here we place P5, here we place P3, and here we place P1. So it requires the third page which is present at the second frame. Okay, so now what will it do? There will be a certain kind of paging implemented. which will constitute of the page table. So in this page table, for each page of the logical address space, so there will be 8 pages altogether: 000, 001, 010, 011. Then again it's 100, 101, 110, and 111. So all these pages of the this represents the pages of the logical address space. Okay, now for each page, corresponding frame number in which this page is present is present in the PTE, page table entry. Okay, so this is called, this is the page number of the logical address space. And it, this page table entry consists of the frame number. Frame number denotes in which frame of the physical address memory this page is present. So the zeroth page is present where it is not present in the main memory, so we keep it as null. The first page is present at the third frame. Okay, so we will place 1 1 here because the first page is placed at third frame. Second place page we don't have any entry. For third page it is placed at the second frame. Okay, now the fourth page we don't have any entry. Fifth page is placed at the first entry. And the sixth page we don't have any entry in the physical address space. And the seventh page is placed at 00 position. Okay, so this page table, from this page table it will come and it will find out that the third page is present where, at the second frame. So from here it will generate this physical address that will constitute of the frame number and the page offset. So this frame number will be taken from the page table entry, and this page offset will remain the same because whatever page will be present, the instruction will be the same accordingly. So this will be 10 bits again. Now from here we will be generating the physical address of this instruction. So it will be something like 010, sorry, just 10, because it's 2 bit. And this is the frame number, and then we have the D, which will be the same as this. So this will be 000 000 010 1. So at the fifth uh, offset, our instruction will be present. So this will remain the same, so D component remains the same, but this changes. And from here we will try to access this page and will bring back to the main memory. So this P3 will be accessed. And here at the fifth position we will be having our instruction that is required for the execution of the program, and from here it will be fetched to the CPU. So this way the flow happens, and you need to understand this flow so that you can answer certain questions related with the paging techniques. And furthermore you can answer some certain question based on multi-level paging or inverted paging or segmentation or segmented paging. So this is very important. And then understanding this page concept, where we have divided the entire logical address memory into certain pages, and each page has its own address for each word. So each word is stored individually in the form of like this. And how many words can be stored in each page is denoted by this page offset. So this denotes where is this word present. So this is very important. 2 raised to power 2 minus 10. So which address you need to access to reach to this part. Okay, so this is called the page offset. Okay, and the page offset remains the same as the frame offset. Okay, this is also very important, right? So this is the D component that we talked about. So I hope some of the links that we talked in the previous video would have been clearer by this video. And let's now start about how this let's see some of the important points, and we will then look into how does this paging happens. So first point is, whenever any process is created, okay, let's say we have created a process, then suddenly immediately paging will be applied. Okay, so whenever process is created, paging is applied. because for any process execution, we need to CPU will fetch some instructions from the virtual memory. It will generate a virtual address that has to be converted into physical address, and that mapping will be done by the paging. So paging will be applied on the process. Okay, paging applied on process, and then page table is created. Page table is created, and base address of page table is stored into the PCB, process control block, stored in PCB. Okay. Then with respect to every process, and with respect to every process will have its own page table. So every process will have its own page table. Okay, this is very important. For each process, whenever it is created, paging is applied, and a page table will be applied, created for that, and base address will be stored in the PCB of that process, and every process will be having uh, its own page table, and page table will be stored in the main memory. Of course, page table of a process is stored into the main memory, is stored in the main memory. Okay, this is very important. Now the fourth point is, there is no external fragmentation in paging. No external fragmentation, because we have divided the entire memory into equal size pages. So no external fragmentation in paging, right? But the internal fragmentation may exist. Okay, and it exists in the last page. The internal fragmentation, the internal fragmentation exists in the last page, and it is considered as p upon 2. Okay, where p is the page size. So no external fragmentation, but internal fragmentation exists in the last page, and it is considered as p by 2, where p is the page size. Maintaining a page size, because we are storing the page table inside the main memory, so maintaining a page size, and for each because it's a mapping between the logical address space and the physical address space, so maintaining the page table is considered as an overhead for the entire system. Okay, maintaining the page table considered as overhead for the entire system, right? And the seventh point is related with the PTE, that is the page table entry. Page table entry, right? So, what does this PTE constitutes of? So, PTE constitutes of definitely the frame number. So, the page table entry will definitely constitute of the frame number, right? Next thing, it will constitute of, along with the frame number, it may consist of valid or invalid bits, right? Next, it will constitute of dirty or modified with whether the page has been modified or not. So dirty or modified bits. Then it will consist of some reference bits. So these are the additional information that is being stored along with the frame number, and along with that it might consist of the page protection bit, or it is also known as the permission bit. So these are the certain other relevant information for the paging. Now we will see some of the questions, but before that, let's see what are these valid and invalid bits. So, dirty modified bits and reference bit and page protection bits. So, page protection bit is nothing but it is used for the security purpose. It tells whether the page is protected or secure from unauthorized access. So, it basically tells about the protection feature of the page, so protected or secured from unauthorized access. Okay, right. This tells about this. Reference bit is nothing but it tells how many times the page has been referenced by the CPU. Okay, how many times page referenced by CPU, right? Then we have this dirty or modified bits, which is and the valid and invalid bit. So let's talk about dirty and modified bit. So dirty or modified bits, so its value can be either 0 or 1. So 0 says that it is not modified. Not modified means whether it has been modified or written by any process or not. And 1 tells whether it says that the page has been modified by the processor as a part of execution. Then again we have this valid or invalid bit. So valid or invalid bit. Now, this can be either 0 or 1. So, 0 suppose that whether page is available in the main memory or not, and 1 is used to say that whether it is, so sorry, 0 says that page not available in the main memory, and 1 says that page available in the main memory. Okay, so these are all about certain other bits along with the frame or translation bits present in the PTE. So this is all about the illustration of how paging happens, and it's illustrate or clears the previous video, some confusions that were present in the previous video. So we will see some of the questions related to paging in the upcoming video. So yeah, thanks for watching, and keep watching. Do like, share, and subscribe. And if you have any doubt or comments, please post in the comment section. Thanks.